Michal is actually abroad, so it means you are stuck with me the whole day, which is actually not a very bad idea today because we have quite a lot of ground to cover. We're going to learn pandas. So last week we learned how to use NumPy, and we learned that it was quite a fundamental and important part of Python's ecosystem. And Pandas is really, I think, on the same line. It's also a very fundamental and important part of the ecosystem of Python. And I think even more useful for day-to-day programming and research, as we're going to see. But first, let's begin with a quick context of where we currently are. So if you remember, in the first week, I discussed the outline for the course. And we had first 3 weeks, which we devoted mostly to basics of Python, and that's behind us. And then for 3 more weeks, we focused primarily on working with biological sequences using BioPython and regex and stuff like that. But of course, we also learned more stuff. And this week, we're beginning a new part, I think, of the course, one of the main parts, where we're going to discuss more advanced data processing and visualization and statistics. So Pandas is really, I think, it really belongs to this category of what I call advanced data processing, as we're going to see. Sorry. OK. So the motivation to use Pandas is to handle what is called tabular data. So essentially tables, which, as you may assume, is quite an important part of data analysis. So it's a very common way to represent data. For example, you might have some data set of samples. Say if you want to do medical research, you want a bunch of patients. And for each patient, you want some different fields, which can be represented as different columns. And we saw that we have the CSV format, which we often use. And I think really it's the most common kind of data that we are going to want to handle. And that is what Pandas is going to allow us to do. Now, we saw that we could use the built-in CSV Python library. But as I said to many of you, I think that this library is actually not a very good one. It's very limited in many ways. And it really doesn't do too much. So we saw that the CSV library will only allow us to separate the CSV file to lines, and then each line it will separate by commas or whatever delimiter we have. So we'll just give us a list of strings, which still requires us quite a lot of effort to then continue to parse. And it doesn't really give us any nice data structure that we want to work with. So in the previous lab exercise, we saw that we could use NumPy to do some more parsing over the CSV. And then we can get a somewhat more convenient data structure, but still that requires quite a lot of parsing. And in the end, it's not the most kind of convenient data structure to work with. And that's, I think, the motivation to use Pandas. So it allows us really to process tabular data much more efficiently. So it's a very strong library. It's very efficient and flexible. And it supports many formats, not only CSV. You can also read Excel files, for example, and many other formats. And as we're going to see, it has 2 main objects which represent the data much better, which are the series and the DataFrame data structures. So we're going to talk about them. And if some of you are familiar with the R programming language, I think you will feel quite at home using Pandas because it's really inspired by it. So in R, we also have data frames. And the way we work in R is very similar to the way we work with Pandas. And also there is the SQL, which is used to query databases, which also was some kind of inspiration to Pandas in the way it allows to query data and to process it and to manipulate it using those basic building blocks. Yeah.
Panda is a type of file, or it's a type of library that
It's a library.
Process data?
Yeah, so Pandas is a library. Okay, it's like NumPy or the CSV or any other package. So it's a library that allows you to parse data and then gives you a data structure, which is nice to work with. And we're going to see that in a moment, how exactly it allows us to work with the data. Yeah. Okay, so the key advantages of Pandas, like I said, it's very flexible and very efficient, and it gives you those nice building blocks, which you can use to then program pretty much everything you want without resorting to pure Python. And like with NumPy, it's also much more efficient in computer time because it actually relies on NumPy to a great extent, and also make sure to use native code for critical code paths. And it's, like I said, it's compatible with NumPy. You have all the D types and slicing syntax. It has a very good integration with Jupyter. So we're going to see that you can present the tables that you parse inside Jupyter. I think that's actually one of the main motivations why Jupyter is such a great environment to do Python programming in the context of research. And it has good integration with Matplotlib, which is the library which we're going to learn next week for visualization. And yeah, it's also a very important part of Python's ecosystem. So not as much as NumPy, but increasingly you see more and more packages being built on top of it. So it is quite important. And it has a very good interface, I think. Sometimes it's not very intuitive, as we're going to see. It takes a little while to get used to it, but I think it's really worth the effort. And if sometimes you're not sure, you can also go to their documentation, which I think is really excellent. It's one, I think, it's an example of really how a package should be maintained and documented. Like you can see everything there, everything is explained. You have many tutorials and examples for everything you want to do. So if at any point in time you're not sure, just go to their website and you'll see terrific explanations. Yeah. Okay, so let's start to speak about what Pandas gives us. So the main object that we need to understand is called a series, which actually represents one-dimensional data. So it's a little bit like NumPy arrays, but it's richer in many ways. Another way to look at it is a series of index value pairs, which are also indexed by position. So it's some kind of a combination between a dictionary and a list, and you can also think about it as an ordered dictionary. So a dictionary where there is importance to the ordering of the elements. And here you can see some example which illustrates that. So in this example, you can see we want to store the number of passengers per month. So you see that the index in this case is just a month in 1 year, say. And then the value is just the number of passengers within this month. And you can also give a name to the series, in this case, number of passengers. And like with NumPy, you have a D type, which refers to the value, not to the index. So here, the D type is an integer, because we want to store integers. OK, so we can access each value according to its index, like we do with the dictionary. We can also access it by position. We can ask for the third element. And it also has very rich functionality, which allows us to do many manipulations on the data, as we're going to see. OK, so that's a series. Now, a data frame is a two-dimensional data. OK, so a series was one-dimensional. That's two-dimensional. And that means basically a table. So like with a series, you can have an index. So in this case, you actually have an index. In this case, you can see an example of different people and different characteristics they have. So a birth month, origin, age, gender. But if you don't explicitly state some more specific index, you'll just get the default, which is between 0 to n-1, like in a list. Now, each column has a distinct type, which could be different. So you can see that the birth month, for example, is, say, a string. The origin is also a string. But the age here is, say, an integer, which is different. And so like with NumPy, if you want something which is not some native, if it's not integer, float, or boolean, you could just state an object. And it can basically contain everything. So you could also support tables with entries which are more complex data types, like sets or lists or dictionary or anything you want, really. But then you will lose much of the richness of the functionality that Pandas gives you. Now, the nice thing about it is the relation between the data frames and the series objects. So what you need to understand about DataFrame is that you can access each time a single row or a single column, and then what we're going to get is a series. Okay, so if you want, for example, to access a row, the values, you will get a series whose values is just the values of this row, and the index in this case will be the column name. So you will get a series which maps each column name to the appropriate value of this row. Okay, and likewise, if you access a column, for example, if you take the origin column, you again will get a series, but this time it maps each row index to the appropriate value. Okay, so we will have Rachel mapping to Spain and Nikki mapping to Jamaica, and so on. Okay, is it clear? Yeah.
So in R, when you're building on the data frame, all the columns and all the rows has to be like equal length. So I can't have like.
Sorry, in NumPy?
Sort of like that, but in R.
In R, okay.
You build a data frame. So column birth months and column age, you have the same length. Is it the same in Python, in Panda? So
Yeah, so you can see that it's a 2D data structure, meaning it has to have a fixed number of rows and a fixed number of columns. Okay, so each column, by definition, has the same number of entries. Yeah. Okay, and finally, you can think about series and data frames as essentially named arrays. So they're quite similar to NumPy arrays. So you can think about series as somewhat equivalent to one-dimensional array, and the data frame to somewhat equivalent to a two-dimensional array, only that you have the names associated with them, so it gives you much more convenient way to access your data. Okay? So let's see code examples and see how it works in practice. So I opened the Pandas notebook. Okay, so we saw that to import NumPy, we just import NumPy, and it's the convention to shorten the name to just NP. When we work with Pandas, the convention is similarly to shorten it to PD. That's just what everybody does. And when you see people referring to PD, you can be pretty much certain that they're referring to Pandas. Now for this example, I'm going to use the ViperDB CSV file, which I think was first introduced on the 3rd week, so you can find it in the Moodle. And to read this file using Pandas, we're just going to use a simple function, which is called readCSV. So we're going to use pd.readCSV and then the path of the file. And that's it. You get a data frame, and you can see that the type is indeed a data frame. Now, if you want to see the table, you can just write the variable, and by default, you see that it will display the data frame as a table, and that's what I referred to when I said that it has a very nice integration with Jupyter. So you can see that it's really nice to look at your data using Pandas and Jupyter together. And you can see all the columns, and you can see all the rows, and you can see that it actually gives also an index, which, like I said, if you don't specify anything, it will just be the number between 0 to whatever. You can see it parsed 419 rows across 13 columns. And each column has its unique data type, as we're going to see. So to display a data frame, we can just write a variable name, like we display everything. But it's actually better to use the display function. So you can, from IPython display, import display. And then the display is like the print function. It shows something to the screen, but in the case of a data frame, it will show it with this more rich and nice way of visualizing it. So let's see some basic functions that we can use with the data frame. So for example, we have the describe function, which for every column for every numeric column. So we also have columns which are textual, which are not described in the describe function. But for each numeric column, you can see some basic statistics of the values of this column. So for example, you can see how many records you have, what's the mean value, what's the standard deviation, the minimum, the maximum, and you can also see the first, the second, and the third quartiles of the data. And this gives you some basic statistics about the distribution of the different columns. Now, very commonly, we don't want to see the whole thing. We just want to see a few rows. So for that, you have the head function, which will just give you back the first 5 rows by default, but you can also specify a more specific number. If you want just the first 3 rows, you will say head 3, and you will just get the first 3 rows of the data frame. And similarly, you have the tail function, which will give you the last 5 rows, or any number you give it. And now to access a specific column, you can just use a square bracket notation to get a specific column that you want. And like I explained, it will give you a series that maps the index of the data frame to the value of this column. So you can see the values of the subunits for each one of the 419 virus records that you have.
We want the different, not the index column to be mapped to the subunits.
Yeah. Yeah, we're going to see that later. But I can show you, it's actually not complicated. So you can actually create a series. You know, actually I will talk about it later. I think it will be easier. But yeah, you can do it. You can change the index of the data frame and also of a series if you want. Now, if you want to access a specific value within a series, then you just give the index within the square brackets. And this is sometimes confusing to people, but you need to understand that this square bracket notation is more like a square brackets of dictionaries, not a list. So the 55 will be the key. It will be the index of the series. It will not be the position or the positional index. Okay, so I will explain it in more details later, but for now, keep in mind that it's a dictionary lookup more than a list lookup. Okay, so this will give you the number of subunits of the 56th virus in this case. Now you can also go the other way, like I said. So instead of querying a specific column, you can query a specific row within the data frame using the loc attribute and then the square bracket notation. So if you go to the location within the data frame of 55, again, think about it more like a dictionary than a list, you will get the values of virus of the 56th virus. Okay, and what you get again is a series that maps the value of each column, sorry, the name of each column to its value within this record. You can see that the D type in this case is an object. You can see that the name is 55, which is just the index of that record. Okay, and you can see all the different attributes of this virus. And again, you can go the other way. So now if you take this record and ask for the subunits, you'll get the same answer as before. Okay, so at the beginning, we first took the subunits column, and then within the subunits column, we ask for record 55. And now we ask for record 55, and within this record, we ask for the subunits value. So it's 2 different ways to get to the same entry. Any questions so far? Okay, so let's look at in more details how we work with series objects. So we will use the same column as an example of a series object. So we'll take the subunits. You can see that the type of subunits is a series. Like NumPy, it has a D type, which is int64 in this case. It has a name, which is just the name of the column. And we can use the len function to get the length of the series, which is 419. Now, like with lists, we can do this slicing operation. But again, keep in mind, so this is somewhat strange. This is a kind of syntax we've not seen before because we have slicing, but with something that is more like a dictionary. So for example, when we ask everything until 5, we actually ask for everything until index 5. Okay, so it's somewhat different than asking it by position.
So if the index was a name,
it would work as well, yeah.
So, okay, so it will give me everything above this name?
Exactly, yeah. So if you give it a name, it will give you everything before this name. Yeah, so this 10 and 20 don't necessarily have to be integers. They can be any index. And then you can also specify a jump, okay? So that really stems from the fact that the series is a dictionary-like object which also has an internal ordering. So you can both use key querying and using some positional requests. And again, notice that if we ask for something that doesn't exist, for example, we ask for record 500, which we don't have, we won't get an index error, which is what we would get with the list. We'll get a key error, which is what we would get with the dictionary. Okay, so it's actually trying to look up for an entry with index 500, and it doesn't find it, so it gives you a key error. And like with the dictionary, you can use the get function to bypass this limitation. So we can ask for 500, and if you don't find anything, then just give us a none. Or we can ask for 500, and if it doesn't exist, then give us a default value, which is something we specify. We also have the sample function, which is a nice and simple way to query a random entry. So it will just give us some random record within the series. So you can see we got record number 368, whose value is this value. And when we ask again, we get a different value. And we can also specify number, and we'll get this number of values. And each time we'll get a series object as the return value. And notice that by default, this is without replacement. Okay, so it will make sure that you don't get the same record twice. Now, if you prefer to work with NumPy arrays, you can just access the values attribute, and you will get a NumPy array which stores the values of the series. So you can see that the array now is just a NumPy array with the same D type, and it's just a NumPy array with those values. And you can also convert the series to other data types. So you can ask to get it as a list if you want, using the toList function, which will give you a list with the values of the series. You can also convert it to a dictionary using the toDict function. And this will give you a dictionary mapping between the index to the value of each entry. And you can even convert it to different formats. For example, you can use the toJSON to get a JSON string of this dictionary. Okay, but most of the time we prefer to keep it as a series object because it offers us much richer functionality than any of the other more native Python data types would give us. And it's also much more efficient to keep it a series. Now, if you want, you can also turn a series into a data frame with just a single column using the toFrame function. So the toFrame will create a data frame with the same index, and the series values will just become a single column of this data frame. Like with a data frame, you can use the describe function, which will give you the basic statistics of the values of this series. So again, the mean, the standard deviation, and different quartiles. You can get some other statistics if you want. You can get the minimum value, the maximum value, or you can get the index of the minimum or the index of the maximum value. And again, notice that this is the actual index. It's not the position. So if the index were a string, you would get strings here as results. So if you access subunits at the index of subunits at the x max, that's just another way to getting the maximum value. Okay? And you can get the mean, standard deviation, the median if you want. And you can actually get any quantile that you want. So for example, quantile 0.14 will give you this value that 40% of the values are below it and 86% of the values are above it. Okay, so quantile 0 is just another way to get a minimum value, and quantile 1 is just another way to get a maximum value, and quantile 0.5 is a different way to get a median. And if you don't specify anything, then by default it will be the median that you get. You have the unique function, which given a series will give you a NumPy array with each unique value appearing just once, okay, in some order. So this gives you all the possible values that this series has. And another very useful function is the value counts. One moment. So the value counts will give you back a series mapping each value to how many times it occurs. Okay, so this will actually give you a series with a different index. Here the values will actually become the index of the series. And the values of the series will just be an integer specifying how many times each value occurs. So you can see that most viruses have 60 subunits, some have 180, and then you get the statistics for different values. And it also sorts the results by the number of values. So you can get all the different values from the most common to the least common. Yeah, question?
I think you said in the beginning that it's the unique value that appears only once, but it's not. Only everyone will appear once, but it can appear in the data a few times.
You mean the subunit's unique?
Yeah.
Yeah, so sorry, maybe I wasn't clear enough. Yeah. Yeah, so it will give you an array with unique values. So even though 60 occurs 237 times, we'll just get it once within this array. So it's like taking a list and converting it to a set. So it's a way to remove redundancy. But again, because it doesn't happen within Python, it's more efficient to use unique than to convert it to a set. You can use the copy function, which given a series will just copy it and give you another copy of the series, which you can then modify without modifying the original series. Okay, so for example, we can now change some entries in the copy series. So we can take a record 55 and change it to 6. And you can see that this has indeed changed in the subunit copy. But then the subunits, the original series, has remained intact, even though we changed the copy. And like with NumPy, you can use some kind of broadcasting to perform operations on slices. So for example, you can take everything between 50 to 55 and change it to 0. And you can see that all of the values changed to 0. Or you can give another sequence of values which is of the same length. So between 50 to 55, we have 5 values, so we can give range 5. And then we change this value to whatever is on the right-hand side. So in this case, it's range. So we just change it to 1, 0, 2, 3, 4. You can even use the plus equals operator to update a slice all at the same time. So we want everything between 50 to 55 to increase by 3. And you can see that this is indeed what we got. So if we want to add a new record to a series, we do it more like we would do it with a dictionary than how we would do it with a list. So in a list, we would use probably the append function. In a dictionary, we would just assign to a non-existent key, and that's what we do with the series. So if we want to create a new record, we take the length of the series, which then gives us the next index, which is 419, and we can give it whatever value we want, and then we'll have this new entry appended to the end of the series. And again, if we want to remove a record, it's like we would do with the dictionary. You can use the del statement and then some record. And here, for example, we delete record with index 417. You can see we have 416 and then right ahead 418. Okay, like with the dictionary. Okay, and again, keep in mind that 417 in this case is what we call a key or a label or an index, but it's not a position. It's not what is called a positional index.
So I can put like strings instead of it if there were names, and I can delete it by names. Fine.
Sorry?
If the key were names, I can delete it by names. I can just give it a list.
Yeah, exactly.
And then every name in the list will be deleted.
Yeah, so if the index is strings, we do the same, like we would do with the dictionary mapping strings to something. Yeah. Okay. Now, in all of these examples, we didn't change the original subunits, we changed only the copy. But notice what happens if we try to actually change something within the copy, sorry, within the original subunits, which is a column in the data frame we began with. So if we try to change an entry in the subunits, you can see that first we get this warning of setting with copy warning. And you can see that now if we look at a data frame that we began with, then this has actually changed the value within this data frame. Okay, so you can see that now record 55 in the column subunits changed to 6. Even though we didn't explicitly change the data frame, we only changed the series, which happened to be a column within this data frame. And this tells us a very important property of Pandas, which is again similar to how NumPy works, is that everything here is by reference. So when we take a column and get a series from a data frame, that's not actually a whole new series. That's actually what is called a view of the original data frame. So when we change something within the series, it will change the corresponding data in the data frame. Okay, so it doesn't really copy the data into something independent. It uses the same data and just give you a different view on the same data. And that's also why we get this warning, because Pandas understand that we try to do something that might have undesired consequences. And actually, when you do that, then Pandas doesn't have any guarantees about what's going to happen. So it's very implementation specific. So sometimes it can, in fact, give you a copy when you ask for a column. But most of the time, it will not be a copy. It will be a view. And that's the reason why you do, when you try to change a series that is derived from a data frame, Pandas cannot really guarantee what's going to happen, and it gives you a warning saying that you shouldn't do that. If you want to change the data frame, then just change the data frame explicitly, and if you don't want to change the data frame, then make sure that you work with a copy of the column, not with the original column itself.
I mean, sometimes it will create copy and sometimes not. Like,
Yeah.
how can it be sometimes?
Just Pandas makes decisions according to, it has all kind of heuristics about, like, in some scenarios it thinks that it might be more useful to return a copy, in some cases it thinks not. So I'm not really sure because I didn't look into the implementation of Pandas, but I suppose it makes sense. I suppose they had good reasons to use sometimes this implementation and sometimes that implementation. But the bottom line is that they don't want you to do that because they cannot guarantee what's going to happen. Okay, so of course, if we want to change the data frame, the right way to do it is just to change the data frame. So we can go to, we can again use the lock attribute, and then we can, like with an array, remember that a data frame is two-dimensional. So we need to specify two values if we want to refer to a specific entry. So we first give the index of the row, and then give the index of the column, which is just the column name. And then we assign the value that we want. In this case, we just want to restore the original value. And you can see that it has indeed been restored, and we don't get a warning. OK, and notice that when we change the copy, then everything is fine, because we work with the copy and not the original data frame. Okay, and like with arrays, we have the same broadcasting rules which apply. So for example, if we take subunits and edit 103, it will broadcast this 103 value across all the entries of the subunits, and we get a new series which is just all the original values increased by 103. And likewise, we can use the subtraction operator, or the multiplication, or the division, or the twice division if we want to make sure that we still get integers, or even the power. So everything works with this broadcasting rule. Now look at this. This can be somewhat non-intuitive. So we take 3 values from somewhere in the subunits, and we then also take the last 3 values. So we have A and B. So these are 2 series with 3 values in each. And you can see the values. And now one might expect that if we just add A to B, so in NumPy, if we took 2 arrays of the same size and we added one to the other, we would get a new array of the same size, with each value being the addition of the 2 corresponding values in the original arrays. And one might expect that this would also apply to series, but then we get something strange. We get a series with actually 3 entries, and then as the value within each. Can you guess what's happened here?
Because you try maybe to add the keys, but not the values, because it works like in pairs. It's not like in regular. The series works in pair like a dictionary. It's not just a list that I can add this.
Exactly, yeah. So a series is like a dictionary. So when you, it does actually support this this broadcasting. So sorry, this vectorized operations. But unlike arrays, which is just by positions because they don't have labels, with series it actually accesses things by the key, by the index. So it doesn't matter in which ordering they are. It will apply to the keys, not to the positions of each entry. So what happens, it sees that the original series has 3 keys. It has 3, 4, and 5. And the second one is different keys. And then it tries to construct a new series, which for each key, it will be the addition of the values within each of the series, which has this key. So for 3, it will try to add 780 for the first series. But for the second series, we don't have 3, so it will take not a number. And then when you add 780 to not a number, you get not a number. And that's what happens across the board here. If we actually want to force that, if we want to make sure that the 2 series have the same index, we can use the reset index function, which will reset the index like the name suggests, and will set the index just to 0 to whatever number of entries you have minus 1. So now both series will have 0, 1, 2 as the index, and having matching indices, you can actually use the vectorized operation on them. Now by default, the reset index function, it tries to also keep the original index. So it will reset the index, but then take the original index and stick it as a new column. And you will get a data frame in this case. So the first column will be the original index. And then the second column will be the values of the series. But very often, we don't want to keep the old index. We just want to drop it. And then we can give drop equals true. And we'll just get a series with the new reset index and the original values. OK, so let's see an example of how we can use these vectorized series operations. So it's very useful when we work with a data frame. So remember that in a data frame, each column is a series, but the nice thing is that all columns have the same index, which is just the index of the data frame. So by design, they have a matching index, and then we can just use vectorized operations on the columns of a data frame. For example, we can take one column and edit the values of a different column, and then maybe divide it by number, and it works like we expected. We then get a series that for each record will give us the average of the inner and the outer radius. And this also works for Booleans. So if we use some operator that is supposed to return a Boolean value, then this will work in a vectorized way. So for example, we can see whether the average radiuses that we calculated, how they compare to the actual average radius field. Okay, and then what we get is a Boolean series that for each entry will tell you whether the sum of the inner and the outer radiuses divided by 2 is smaller or equals to the average radius field. And you can even use the value counts on top of that, and you can see that for 412 entries, the answer is true, and for 7, the answer is no, meaning that the average radius tends to be more similar to the outer radius than to the inner radius for most viruses. And like with NumPy, we can use the or any functions to check whether everything is true or some things are true. And we can also use it for splicing. Okay, so now what we do, we take subunits series and we access it within some Boolean series. So again, when you do that, then Pandas requires you that the two series will have the same index, essentially. And then it will just give you the sub-series of the original series where the values of the mask of the Boolean series is true. So in this case, we use the not operation to reverse that. So we only take the 7 values which were false at the beginning. And then we get the subunits of those values. Okay, so we can also do that in place. We can do all these operations in just one line of code if we want. So we can do something like, let's do it like this. We take df for subunits where, sorry, I got the insert. Okay, and then we want that where we can take this series and compare it to this series. But we actually want the not, so we'll reverse that. Okay, so now just in one line of code, we work directly with the original data frame. So we take the subunits column, and from that we query all the records that have this condition satisfied, that the average between their inner and outer radius is bigger than the recorded average radius.